Good afternoon. Selamat berpuasa for our Muslim students. Okay, we'll continue with the stability topic that we have started on Tuesday. We have defined the stability, what it means. We have looked into the conditions of getting the stability to set up the characteristic equation 1 plus g, look at the roots of the equation and check the location of the roots of the equation. If the roots on the right half of the complex plane, then we'll get exponential terms and the system will be unstable. If not, it will be a stable system as from the stability criteria. And this is the complex plane that we can see here. Example of the complex plane, we can see from the roots on the right, it's unstable, on the left is stable, on the axis. It depends if it's on the left of the real axis is stable, right of the real axis is stable, and so on. So we have seen that in our class before. This is an example given for a second order system where we get the characteristic equation, and looking at the characteristic equations, we look at the roots of the equation and then we solve whether it's on the right or the left plane. Okay, this is easy way, fast way, but as you can see, depends on the number of roots of equation. If the roots a lot, then it'll be quite a tedious method. Of course, we can use MATLAB to solve and get the roots and solve it, but there are also some specific and organized way of getting the roots of the equation from our next topic, which is on the Rouse stability analysis method. Okay, the Rouse test for stability, as you can see here, is basically a purely algebraic method for determining the stability of linear control system. There are few steps in the procedure. First thing is to write the characteristic equation in the polynomial form, as we have done before, to get the roots of the equation. And basically, in this case, an coefficient, and to make sure the first of all a is positive. If a not negative, we multiply all by -1 to make positive. In this form, it is necessary that all the coefficients be positive if all of the roots are to lie in the left half plane to make it stable. If any coefficient is negative, system is unstable. So if you try to arrange, make them positive, but somehow one of them is negative, then definitely the system is unstable. You don't need to go further. That's it. It just says that system is unstable. So the Rouse test is not necessary to answer the question of stability in this case. Yeah. So if it's all positive, then it's still not sure yet. We're still not sure if it's stable or not. We have to continue with the Rouse array method, as we will see next in this Rouse array method, where we have we have to set up the Rouse array in such a way that we arrange the coefficients in the first two rows of the Rouse array. The 7 coefficients in this case. The first row contains the A0, A2, A4, the even coefficients. The second row contains the odd coefficient A1, A3, A5, and so on. You can see here. And the other coefficients in the other rows are just given by this formula here. We don't have to memorize. It's just cross multiplying A1 with A2 for B1, A1, A2 minus A0, A3 over A1 coefficient here. B2 is A1, A4 minus A0, A5 divided by A1. So just cross multiply and divide by the coefficients A1. For the next rows, it's just like that. C1 is B1, A3, B1, A3 minus A1, minus A1, B2 divided by B1. And C2 is like that. B1, A5 minus A1, B3 divided by B1, and so on and so on. You will fill in the n plus 1 rows. In this case, the array is filled for n equals to 7. The array is prepared in the same manner for any other value of n, and generate the n plus 1 rows. And for n even, the first row has one more element than the second row. So this is the Rouse array that you first have to fix or fill in before you can apply the next step, the theorem of the Rouse array. Okay, the Rouse test theorems is given by this theorem, as you can see. This first two theorems are the first important ones that we need to apply in this case. And it's basically the first theorem says the necessary and sufficient condition for all the roots of the characteristic equation to have negative real parts, it to be stable, that all elements of the first column of the Rouse array be positive and non-zero. is the first condition for stability. And if some, second theorem says, if some of the elements in the first column are negative, the number of roots with positive real parts, which means how many roots make it unstable, is equal to the numbers of sign changes in the first column. How many sign changes in the first column? That will tell us how many roots are on the right of plane and make the system unstable. Okay, this is the first two theorems that apply. Normally the third theorem is a special case, may happen, may not happen. If there's one pair of roots on the imaginary axis and all other roots are in the left half plane, then you will find that all elements of the n row will vanish and none of the elements in the preceding row will vanish, which means that some rows will have zero coefficients, zero values in the above array, and the location of the imaginary root can be found by solving C(s) squared plus d, where coefficients C are d and d are the elements of the array in the row before that, the n minus 1. The rows that have the zeros are n, and the rows before give you the coefficient C and D, and you can solve it to get the location of the roots of the equation. These are the theorem, but the first two theorems is the one that you have to apply normally. Once you have the Routh array, basically for this example, quadratic equation, this is the polynomial equation you get, 2 power degree 4. So you arrange the coefficient, the even and the odd. So the 1 and 5 comes in the 1, 5 and 2 comes in the first row. The 3 and 4 comes in the odd one comes in second row, and then the other coefficients are just by multiplying 5 times 3 divided minus 1 times 4 divided by 3, you get 11 over 3. The next one is 3 times 2 minus 0 and minus 0 times 1 divided by 3, you get 6 over 3, and so on and so on. You will fill in the arrows. It's 5n plus 1 rows, so fill the rows to get the array, and from now you can see, you apply the theorem to see what it is. It's all up positive, so the system is positive. The elements in the arrays are formed from this formula b1 and b1 and so on. Since there's no change in sign of the first column, which means there's no negative, there are no roots having positive real parts, and the system is automatically stable. So this is a very simple step of applying the Routh array to find the stability of the system, and if it's unstable, how many roots on the right plane, right plane, by using the sign changes and so on. So this is the Routh method of checking stability of system, and so you can just use this, or you can, if you have, you can find the roots of the equation, fine. If the roots of the equation is to find is tedious, you can use this Routh method to find whether it's stable or not, how many roots on the right of plane or on the left of plane, and then see whether the system is stable or not. So stability is important. It's not just getting the set point or disturbance change, but you, to get the disturbance, set point and disturbance, you have to make sure first the system is stable. It can be affected by the tuning constants, and this method can also to use to get the right tuning, normally for just for the KC, right? From the KC to give stability. What is the KC that will give stability? Stability means what is the KC that will give the first column all positive. It's possible by this way. When we see the examples, you can do the tutorials given in chapter 13. We are covering chapter 13. We are giving you two questions that will make it understand this part very easily, and we will maybe go through that one, and you can see that. So a simple method to use to check stability of closed loop.